In this video, we're going to learn about combinations and probability. A combination is like a permutation, except the order of the outcomes doesn't matter. So here's a general formula for a combination based on the formula for a permutation, where the number of combinations is equivalent to the number of permutations divided by r factorial, where r is the number of choices made. So this factorial, here's an example. 5 factorial means multiply 5 times 4 times 3 times 2 times 1. For a longer description of how these are related, you could look at your media lesson packet. Here we're going to apply these ideas. So use combinations to calculate the following probabilities. Write your answers as percents rounded to 3 decimal places. So in the first one, we're told a committee has 13 members. 4 members must be chosen for a subcommittee. So you're choosing 4 people out of the 13 people. And how many ways can the 4 members be chosen for a subcommittee from the 13 members? So notice I have 4 spots ready here. If we were to find the number of permutations, which is part of the combinations formula, we would say, well, I have 13 choices for the first person, then 12, then 11, then 10. Okay. But what's different about a combination is that notice here we're choosing 4 people for a subcommittee as opposed to the example where we chose 4 people for, say, president, vice president, secretary, and treasurer. Here we only care if the people are on the subcommittee or not on the subcommittee. Whereas with the president, vice president example, Amy being president and Bob being vice president is different than Bob being president and Amy being vice president. So the way we account for that difference is we find the permutations, so this is the numerator, okay, of 13p4, but then we're going to divide by 4 factorial, and that cancels out all the overcounting. So we have 13c4, the number of combinations of 13 objects taken 4 at a time, equals, let's just write the whole thing out, 13p4 over 4 factorial, which is 13 times 12 times 11 times 10 over 4 times 3 times 2 times 1. Okay. And let's cancel as much as we can. So 4 times 3 is 12, so I'm going to cancel the 4 and the 3 with the 12. And 2 and 10 share a common factor of 2. That leaves a 5 on top. Okay. So this number of combinations is 13 times 11 times 5. And again, there's a button on your calculator that will do this directly, but I think it's useful to see how these multiply out. And we get 715 different ways we can make such a committee. Okay. And then we're going to use this as our sample space for the next few probability problems. So let's look at the next one. There are 3 members in the Human Resources Department. If the subcommittee must have exactly 1 member from Human Resources, what is the probability that a randomly chosen subcommittee will meet this requirement? Okay, so we already know the size of the sample space, that's 715. We're going to put that over here. Now let's find the number of elements in the event space, and that's if we have exactly 1 member from Human Resources. So I have this set up here. Notice I have a Human Resources choice, and then we have to choose 3 people not from Human Resources. So in a way, this is kind of like the fundamental counting principle, where the human resource people is our first choice and this is our second choice. This will be a combination, and this we could consider a combination, but we could also just say there are 3 people from human resources. So for the human resource people, I have 3 choices. Okay, that's actually the same as 3 choose 1 or 3p1. Okay. Now let's choose the non-human resource people. So remember it said exactly 1 member. So now we're going to look at, well, there's 13 members in total. So there's 10 members that are not from human resources. So that's 10 times 9 times 8. And we're going to need to divide this by, since it's a combination, 3 factorial. So let's write this out here. So we have 3 times 10 times 9 times 8 over 3 times 2 times 1. I'm going to simplify a little bit. The 3's cancel, and 2 and 8 have a common factor of 1. And if we multiply, we'd have 10 times 9 times 4. Well, that's 360. Again, feel free to do that on your calculator. Okay. So there's 360 such committees where there's exactly one member from Human Resources. So that's our numerator. And now let's write that as a percent. 360 divided by 715 times 100. And that's 50.35 rounded to 2 decimal places. 50.35%. Let's box that since that's our final answer. Let's look at the next one. So we still have our committee. We want 4 members for a subcommittee, but we're going to be given another restriction. So there are 4 members in the IT department. If the subcommittee must have at least 1 person from IT, what is the probability that a randomly chosen subcommittee will meet this requirement? Okay, so this one is a little bit trickier than it may look, but we're going to be trickier. We're going to use another trick to kind of get around it. So notice it says at least 1 person. Remember the last one said exactly 1 person? Okay. And at least 1 person can be complex because we'd have to count exactly 1 person from IT, exactly 2 people from IT. We're choosing 4 members, so it could be 3 people from IT or all 4 members. Okay, and we could count them all exactly and sum up their results. Okay, if you try to just pick one IT person and then pick others, you don't know which one you picked from where. So this is a general way to do this, but the trickier way to do this, and we saw this in another problem, is that the complement of at least 1 person from IT, so remember complement, is no people from IT. And then if we find the probability of no people from IT, at least 1 person would be 1 minus the probability of no people from IT. Okay, so this is the direction we're going to go. Okay, and again, whenever you see something, we've done at least problems before in probability when we had a bunch of things listed and we could count them. But since we're doing fancier counting now, if you see an at least problem, you might want to look for this option to make your problem more simple. Okay, so let's find the probability of no people from IT. Well, let's down here, we know that there's 715 total possible committees, and no IT people means that we have 13 minus 4, 9 people to choose from. We have 4 choices to make. And here we have 9 choices, 8, 7, 6. And again, we have, since we made 4 choices, this is the number of permutations. For combinations, we'll divide by 4 factorial. So this is C and 4. Okay, so let's compute this. 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. Again, you can do this on your calculator. Just be careful with parentheses. Here we have 3 and 2. That cancels out the 6. Here I'm going to cancel out the 4 with this 8, and that leaves a 2 on top. So on top we have 9 times 2 times 7, which is 63 times 2, which is 126. Okay, so there are 126 committees with no IT people. Okay, so let's write this as a decimal and then we'll do the subtraction last, or as a percent. So 126 divided by 715 times 100 is 17.62%. So 17.62% of the committees have no one from IT on it. So at least one person from IT would be, now we're going to use, instead of 1, since we're writing this as a percent, we're going to do 100% minus 17.62% equals 82.38%. And that is our final answer.